All right, welcome to this video for Material Science 410, looking at some additional materials for the experiment where we investigate corrosion and coatings on metals. So as part of our discussion here, we'll first look at the two main methods used to galvanize steel. And first, of course, touch on what galvanization and a coating made from galvanization is. So a galvanized coating is one of the primary means for inhibiting corrosion of metals. You may have recognized galvanization on various metals, as we see this sort of granular, leaf-like, or almost fern-like pattern on many metals, indicating that a coating of zinc has been applied to such a metal. Further, you'll see that when the coating is very, very thick, generated by a hot dip method, that we're going to see crystallization of excess zinc, and that is going to lead to the grains that are you may have seen on galvanized steel, for example. So the function of this zinc coating is ultimately to act as a tough bonded barrier and one that covers the complete surface and will seal the steel or the metal structure away from the environmental kind of environments that are often very corrosive. Okay, so this sort of acts like a barrier or a skin around the structure at the very least. The bonding is at the metallurgical level, or that is to say it's often alloyed, so the bonding is very good if the zinc has been applied correctly. Further, the zinc, as we'll see here, is a sacrificial coating in that it would want to corrode first rather than the metal beneath it, given how strongly reducing the zinc is. And in fact, if there is any metal corrosion beneath the zinc will sacrifice itself to restore that oxidized metal back to its original oxidation state, zero state. So what we see in steel are, as we mentioned a moment ago, often an exterior coating that is pure zinc and the base sort of metal well below it. And often in the interior, we see alloy or intermetallics forming depending on the method. Okay. And so the hot dip method is the one that tends to generate the situation where we have a lot of excess zinc on the surface in the form of pure zinc, as we'll see. Okay, so galvanized steel can be generated from two main methods. The first one that's common in industry is what's called electrogalvanization. This leads to a relatively thin zinc coating on the metal object. And it's generated by an electrochemical reduction of zinc ions from an electrolyte to generate that zinc metal on the surface. Okay, so you can see here zinc ions. This would be found in the electrolyte. Undergo an electrochemical process where they're combined with electrons from the completed circuit to reduce zinc ions to zinc solid as a coating on the metal. So long as the structure is conductive and we can connect leads or wiring to it, we can consider applying zinc as a uniform coating around it, such that wherever the electrolyte has enveloped the metal. And so a process here where, say, a steel belt or strip is sort of passed through rollers that are acting as an electrical contact point, can bring that steel strip into the zinc electrolyte that we see here. So this is sort of a bath of zinc electrolyte. Some anodes complete the circuit. So the anodes are shown here. The steel strip is acting as the sort of cathode as it passes into the bath. Anodes here are typically zinc solid to restore any zinc ion that is lost in the process. Okay, so here's our zinc 2+ aqueous that we saw a moment ago. and that is going to be applied to the steel strip as it passes into this electrolyte bath. After some time in the bath, of course, if this were a continuous process, that steel strip is removed and passed outward as product for clipping or cutting to produce the freestanding product. What's important and interesting here about the electrogalvanization process is that the current passed is correlated to the amount of zinc that's applied. And this is calculated by Faraday's law. So here you see Faraday's law, where the mass of the zinc applied goes proportionally with current, I, in this equation. To give you further analysis of this equation, you can see we can look at the units and the other factors. So we have T, the time of the deposition. So that could be the residing time in the electrolyte bath. We have the atomic weight of the metal being applied, in our case zinc. So here's the atomic weight. The number of valence electrons that are transferred. Okay, so this is evaluated at the atomic level. How many valence electrons are needed to transform the electrolyte metal into its metal zero state? And we have Faraday's constant, which is 96,485 coulombs per mole of electrons transferred. And we have M, the mass of the zinc metal applied to the structure. So putting this all for just a quick unit analysis, you can see here that the first term is current, which would be coulombs per second is the amp. The second term is time, so there's seconds. And the third term is grams per mole for the atomic weight. This is divided through by a unitless value for N, so that is simply integral integers, 1, 2, 3, or 4, depending on the ion being used. So in our case, zinc is a 2 electron transfer process. So that would be unitless. We'll put a 2 there for its place. And then the final factor here is Faraday's constant, which is coulombs per mole. And you can see here in canceling out all of the units, coulombs cancels coulombs, per second cancels seconds, the per mole cancels the per mole, and we're unitless here, so we end up simply with grams. So this, in fact, works. Faraday's law here can predict the amount of zinc applied in grams, given that we've monitored the current and the time of this electrogalvanization process. Okay, a second galvanization process here is the hot melt process or hot dip method. So here what is done is typically a metal structure, steel for example, is first primed with various steps for an application of molten zinc to its surface. Notice that this is molten, very high temperature here, about 450 degrees C, to render zinc into its liquid form. And the steps ahead of that prime the surface for various chemical steps. Again, the final structure here is going to be rich in excess zinc, and so we'd expect pure zinc to exist at the surface with grains owing to the crystallization of that zinc after the quench step, typically used by a water dip or executed by a water dip. So the hot dip method generates a thick coating of zinc to contrast what we saw in the electrogalvanization process, which is typically generates very thin coatings governed by the Faraday's law. Okay. So the first step here is an alkaline degreaser to remove paint and oil and other sort of surface contaminants. Okay. Second, there's an acid pickle. So this acid dip step here removes any rust, any oxides. Typically oxides are soluble in low pH acid. And this readies the surface to receive a zinc coating. Okay, and after this acid step, the surface is very reactive. It will rapidly generate new oxide layers as it resides in air. So transitioning the material from the acid pickle to the sort of hot flux step in minimum amounts of time is advantageous. And so this hot flux of ZaC, zinc ammonium chloride, formula shown here, allows for the application of a very thin coating of zinc to be applied to the surface and to handle any residual oxides that are forming. So this acts as a bit of a zinc priming step to allow the additional zinc of the hot melt step to really bond to an alike surface that is already containing some zinc. Okay, and then we mentioned that we dip the final sort of prime structure after the ZaC step into molten zinc for a final thick application of a zinc coating from a liquid state at about 450 degrees C. Quenching, of course, is necessary to bring the structure back to room temperature and to rinse off any excess, and that's typically done here with water. The cross-section of the hot dipped sort of structure has been investigated. And so here's a nice electron micrograph where we've used scanning electron microscopy to interrogate the cross-section. You can see here that in fact there is a very much a layered structure, so that the steel is found below. Okay, so this was the surface of the structure down below. Notice that it has 0% zinc in it. And then as we move up towards the surface of the ultimate structure, we start to see the zinc presenting itself, and we see different phases. Here we have a gamma phase, a delta phase, a zeta phase, and an eta phase that take us all the way through to the pure zinc at the top. So the eta phase is pure zinc. So these roughly kind of 4 layers are kind of shown here, and of course the pure steel is extending down below. When we consider what those composition bits of information of these coatings mean, we often turn to a phase diagram, which you may have seen in prerequisites for this course. So here's the phase diagram for iron zinc, showing a temperature y-axis. And so if you recall, we said that we typically apply zinc to metal structures like steel at about 450 degrees C, so that's about here. And we would expect that by walking laterally here in this territory, we'd eventually see the phases of the zinc iron system that may be present at the surface of these metals based on iron. And so at the outermost level, when we have pure zinc, we're at the limits here, and so that's the eta condition for pure zinc. And then as we walk to the kind of next territory in the phase diagram, that's where we're going to see the zeta phase, which is typically about 94% zinc, and that is kind of shown here, where there's an exact stoichiometry of zinc 13 to every iron atom. And so this is sort of an intermetallic type situation for the mixture of the two metals in a unit cell. Okay, thereafter at about 9 to 1 stoichiometry is the delta phase, and so we're going to see that showing up here as the next territory in the phase diagram. And that again is the delta phase here, an intermetallic of zinc and iron in that unit cell. And then capital gamma here is our next kind of phase. This is about 76% zinc, and we see that area sort of starting around this condition here, which is our intermetallic of zinc and iron again with a different sort of unit cell defined there. Okay, so again, we can turn to the phase diagram to help us understand that different lattices of these two metals, zinc with iron, will exist in the material, and that may present itself in certain characterizations that we used. Here, the electron microscopy is distinguishing those layers based on the electron density of the two different metals and their packing pattern in the unit cells, and we're seeing contrast in the electron microscopy image. So clearly the atomic arrangement and packing of the zinc and iron here has presented itself as an opportunity for characterization in this SEM micrograph. Further, other techniques that may be surface sensitive or have certain penetration depth may interrogate only the zinc, or depending on the thickness of this eta phase, may only show just pure zinc. So consider this diagram when you're reflecting on any X-ray diffraction data to consider whether or not the XRD data will show characterization of just the topmost layer or perhaps layers below, given its penetration depth and the scale shown here in this image. Okay, so in order to sort of reverse engineer and understand a galvanized coating on steel, we'll need to understand the corrosion and stripping chemistry of the galvanized steel samples. So galvanized steel will eventually corrode, as you might expect, and this will occur under exposure to water, but the galvanized layer will kind of extend the useful life of that underlying steel because of its electrochemical kind of action on that metal structure. So the galvanized layer, for us in this lab, we'll see can be rapidly stripped with acid. Okay, so this is to say that we recognize that zinc solid can be digested away using HCl. So our reaction is going to be zinc solid plus HCl, aqueous, to make products. And this tells us that we're going to make ions and gas. So here's a moment for you to reflect on what we've shown in this equation to predict what the products would be based on the observations for ions and gas forming. So take a minute to list your products and see if you're correct by resuming the video in a moment. Okay, so hopefully you've considered the most likely gas to form given the reagents that we've listed here. And that is, in fact, we're going to see H2 gas formed from this reaction. So we're going to use the reductive potential, the electrons built into zinc, to react protons from HCl to make H2 gas. Okay, so that's one product. And if you weren't able to determine this product, at this point you could pause the video and see, based on deduction, if you can determine the final product that we expect here. Okay, so thereafter we're expecting zinc chloride, aqueous, as our final product. And the process of balancing here would tell us that we need 2 HCl molecules to give us the dimer of hydrogen and hydrogen gas, and the 2 chlorides in zinc chloride, aqueous. Okay, so that is what happens when we expose galvanized steel and remove the zinc by an acid etch. Okay, now how about the role of zinc and iron and how it might work by a similar method? Okay, so we've seen that zinc is very good at reducing acid in an acid etch step. We might expect zinc to be able to play a role in helping maintain iron at its iron zero state, like it worked on protons to keep them in an oxidation state of 0 in H2 gas. Okay, and we've already addressed the reaction with acid above, and we'll now move on to discuss this iron topic. So for this, we often turn to the standard electromotive force series, or the standard electrode potential table shown here. And this lists electrode half reactions all as reduction reactions. So we're going to consider all ions possible and how they might combine with appropriate number of electrons to produce products that are reduced. Okay, so gold 0 here has been reduced from a gold 3 state by combination with 3 electrons. This is similar to what we saw a moment ago for the electrogalvanization process, where zinc ions from electrolyte were combined with 2 electrons to give a zinc coating that was thin. Okay, so as we consider the activity on iron, we can look at these half reactions to predict whether or not the process will be spontaneous. So here, thinking about iron, you should be able to point out 2 half reactions that are relevant in dealing with iron, represented by symbol Fe, and how they'll interact with zinc solid here. So take a moment to find those in the chart and resume the video once you've had a chance to spot them. Okay, so yes, of course, we're talking about these 2 reactions here. We can see that iron 3 can be transformed into iron 2, and there's a standard electrode potential associated with that shown here. Okay, so that is to say, if we wanted to reduce iron 3, we would need to provide 0.77 volts of potential relative to this starting point, which is the hydrogen reduction reaction, H plus with 2 electrons to make hydrogen gas. Okay. The other one here is now that iron 2 can also be further reduced, so 2 electrons can go into iron 2 and make iron 0 down here at negative 0.44. Okay, so if you want to transform iron 2 all the way into iron 0 metal, you're going to need negative 0.44 volts of applied electrode potential to drive that process. And this is, of course, relative to the 0 point here, which is, again, protons going to hydrogen gas. Okay, and we see here zinc is the other kind of half-cell reaction of interest. And zinc here has a very electronegative, a very negative value here on its standard electrode potential of 0.763 volts. Okay. So these half reactions can be combined to predict the sort of galvanic cell electrode potential and predict ultimately whether or not a process is spontaneous. So we saw a moment ago that zinc ions could be transformed, zinc could be transformed into zinc ions with acid. And that was a spontaneous process that would digest the zinc. So let's see if we can use the information here to show that. So let's try to sneak that in the little box over here. We're going to take this half cell reaction and flip it. Zinc solid is going to become zinc 2 plus ion plus 2 electrons. So having flipped that, I have to flip the sign on my value here. So my sign, I'll make a little line here, is going to be now 0.763 volts. Okay. Make some room for some of the subsequent half reactions. Okay, so I've now just shown the zinc digesting into zinc ion. And then we want to consider the proton reduction reaction that was representative of the acid. So here, H plus, and of course there are 2 of them, plus 2 electrons is going to form H2 gas. And that was a 0 volts result there, as we see in our table. So the sum of these two is zinc solid plus protons, 2H plus, to form H2 gas and zinc ion 2 plus. Okay, this is the exact equation we had a moment ago when we discussed HCl corrosion of the galvanic layer. We are missing the chlorides, which was HCl and zinc chloride, and those are largely spectator ions in this process. The sum of the volts here is simply the addition of these two, and this process has a E cell, therefore, of this. So this is the value of E naught, where naught represents standard conditions of 1 molar concentration and room temperature and atmospheric pressure. So here we have our E cell for this process. This is what we have above. And so when E cell is positive, like we have in the first bullet condition, we see that the Gibbs free energy for the standard condition process will be negative. So when the Gibbs free energy is negative, we have a spontaneous process. So if the E cell values, by the analysis we just did, is positive, we can expect spontaneity in the process. So again, protons plus in the form of acid plus a zinc coating on a metal will digest spontaneously, and we take advantage of this for our lab. Okay, some additional electrochemical considerations that we can apply to the galvanic kind of roles of zinc on steel are shown here. So here zinc and iron end up forming a galvanic couple. So that is to say that they kind of electrochemically communicate and will take advantage of the reduction potential of zinc. So we see in that chart that the reduction potential of zinc is greater than iron. Okay, so zinc is down here and it's further down on the product side of this chart. And so that's how we recognize that its reduction potential is greater than that of pure iron, which is above. So we would anticipate that electrons would flow from zinc solid to iron and find any iron ions that have been generated by the initial processes of corrosion. Okay, so here's the zinc solid coating. Any surface located iron ions that have been generated by the initial stages of corrosion would respond to the electrons coming from that zinc coating. Okay, so the zinc coating is going to sacrifice itself, make zinc ions, liberate electrons into the metal. Those will then cycle through the metal to any sites where some iron ions are found and bring them back to their iron zero state. The potential values from our chart are above, so we had to reverse that of the zinc standard reduction half cell reaction on the previous chart. So here's that same value again, 0.73 volts positive this time. And we'll see here we're using the iron 2 equation right here. So 0.44, we are not flipping that, so we'll just keep that value the same. The sum of this is now a positive value at 0.32 volts. So recall that delta G naught is equal to negative NFE naught for the cell. Our cell value here is right there. Faraday constant is F, and the number of electrons transferred in the process here is 2. And this would predict that the process should be spontaneous. Okay, so you can see here how zinc acts to spontaneously bring any iron 2 ions back to their iron 0 state to protect that iron structure. This is how we justify saying zinc provides a sacrificial coating and acts to provide electrons to the iron itself so that the iron won't get oxidized. Okay, so to show that in the diagram, we have two roles for the zinc. Not only is it simply a physical barrier to keep the environmental conditions away from the steel below, but also if there are any small areas of iron 2 ions being generated, they're immediately brought back into an iron 0 state by the action of electrons from zinc metal at the expense of generating zinc ion 2+. Okay, and so just kind of showing you all that again. Here's our net result. This was the sum. We saw this a moment ago, spontaneous reaction. And so you can see here that when zinc is applied to a metal structure, like the sort of leg on a boat, that the zinc metal here will be sacrificed slowly over time to help maintain the iron here in an iron solid zero oxidation state. And eventually the sacrificial zinc anode would need to be replaced, and one would purchase a new part there for under $10 to maintain that iron on this nautical vessel as an iron 0 state. Okay, so in lab you can see here that we're going to investigate galvanized steel coating on steel. We're going to use an acid strip to digest away the zinc coating. We've justified the electrochemical steps there a moment ago. This will lead to a weight change and certainly transform the optical microscopy result of the zinc. So we'll lose that leafy granular structure that we saw in the diagram a moment ago, and we'll expose bare steel in doing so. So we'll end up doing characterization before and after this stripping process. We'll use microscopy to look at the surface grain structure. We saw it in a slide earlier in this video. We'll also use SEM to kind of look closely at that surface before and after this this acid stripping step, and look also at the cross section there as well. And then we'll compare the elemental compositions, that is the content of zinc, the content of iron at the surface and in the cross section, and use energy dispersive X-ray spectroscopy, EDX, here to help us do so. This should help us prove whether or not we've removed all the zinc and exposed more of the iron below. X-ray diffraction, XRD, is a method that can interrogate the crystal structure or structures that are present. And so we may see that the crystal structure of zinc may be present at the outermost surface. Perhaps some of the other intermetallic phases below might present themselves in the XRD. And certainly after an effective stripping, we might see a new lattice pattern develop in that XRD data owing to the metallic iron or steel that is below. And that being the new surface and new material interrogated by the XRD technique. All right, and that should be how we're interrogating the galvanized steel coating. In a follow-up video here, we'll discuss how we'll investigate and look at the fundamental materials chemistry and engineering of brass and generating